material. Now this is the coolant. As you can see here, this is the aluminum cladding, which is the inner sphere. And from here the temperature is TF. The radius from the outer to inner is the RF, and the inner to outermost sphere is the RC. The temperature near the interface is the TC, and the outermost sphere temperature is the T0, which is the air temperature. Discuss the boundary conditions. At interface, the continuity of temperature and the heat flux normal to the interface are required. At interface, the continuity of the temperature and the heat flux normal to the interface are required. Now the first, at R is equal to the RF, QRF is equal to the QRC, which is the interface boundary condition. Now the logical boundary condition, at, so the logical boundary condition at R is equal to 0, QRF is not infinite. Second boundary condition, at R is equal to the RF, QRF is equal to the QRC. Now the boundary conditions. Boundary conditions. First one is the temperature may be specified at the surface. Temperature may be specified at the surface. Now second one is the heat flux normal to the surface may be given. This is the equivalent to specifying the normal component of the temperature gradient. The heat the heat flux normal to the surface. May be given this is equivalent to specifying the normally component to the temperature gradient. From the desired equation, at R is equal to the R F QRF is equal to the SN naught R by 3 plus B by RF square R cube by 5 by this QRF at RF QRF is equal to the SN naught 1 by 3 plus B by 5 R to the power 5. Now from this, R to the power F. Now from this, the Q1C is equal to the C1C by R square, which is by applying the R is equal to the RF. From this, we get the C1F divided by RF square. Now further, if you go the QRF, which is this equation, QRF is equal to the SN naught 1 by 3 plus B by 5 R to the power F. Now further, if we equate these two equations, we get the C1C divided by RF square is equal to the SN naught 1 by 3 plus B by 5 RF. By equating this equation, we can get the C1F is equal to the SN naught 1 by 3 plus B by 5 RF into RF. So we get the Cn is equal to the Sn naught 1 by 3 plus B by 5 RF. At the interface, the continuity of the temperature and the heat flux normal to the interface required. Now the equation is QRF is equal to the Sn naught R by 3 plus B RF का whole square R cube by 5 plus C1F divided by R square. Second equation is QRC, which is equal to the C1C by R square, which we have derived before the equation by integrating the equation 1 and equation 2. We got this equation after the integration. At the solid fluid interface, the normal heat flux component may be related to the difference between the solid surface temperature T0 and fluid temperature TB. QRF is equal to the Sn naught R by 3 plus B by Rf R cube to the divided by 5. QRC is equal to the Sn naught 1 by 3 plus B by 5 Rf to the power cube divided by small r square. Now from this, substituting the Fourier's law of heat conduction. Substituting Fourier's law of heat conduction. By substituting the Fourier's law of heat conduction, QRF is equal to the minus KF dTF divided by dr. QCR is equal to the minus KC dTC divided by dr. From this we get the minus K. From this we get the minus K. Minus Kc dTc by dr is equal to the Sn naught R by 3 plus R by F R cube divided by 5. From this we get this equation. Now we have further rearranging this equation, we get the dTc by dr is equal to the Sn naught 1 by 3 plus B by 5 Rf 5 to the power r square. Now integrating this rearranging equation, we get the by integrating rearranging the equation, TC is equal to the Sn naught by Kf. TC is equal to the Sn naught by Kf R square divided by 6 plus B divided by Rf R to the power 4 20 C1F. So we got this equation by integrating this equation. After the integrating, this is equivalent to the component gradient Now the third one is at the interference the continuity of the temperature and of the heat flux normal to the interference required. By applying boundary condition to this equation, we get when the R is equal to the 0, we get the QRF is equal to the Sn naught R by 3 plus B RF square R cube by 5. Now here C1 F divided by R square. Now here R is equal to the 0, but this term is the infinite, which doesn't exist. So due to this, we can't define this term. So due to this, we have to do 0 for this term, so that the Sn naught R by 3 plus B by RF square R cube by 5 plus 0. Now here C1 is equal to the 0. Last equation is Tc is equal to the Sn naught Kc 1 by 3 plus B by 5 RF to the whole 3 divided by R plus C to C. TCF is equal to the Sn naught divided by Kc 1 by 3 plus B by 5 RF divided by R plus C2F. Now these two equations we have got from the previous solutions. Now the boundary conditions. Boundary conditions the temperature may be specified at surface, at a surface. Now the second condition, which is the boundary condition at interface, the continuity of temperature and of the heat flux normal to the interface are required. So from this, the H R is equal to the RC, TC is equal to the T naught. At R is equal to the RC, TC is equal to the T naught. So
थोड़ा मेरे इधर से कर ऐसा मुझे चेंज नहीं होगा ठीक है 3 2
अरे मैं स्टार्ट
yeah, you have actually got a formula to describe this. Sn is equal to Sn plus 1 plus R by Rf whole square. So Sn is just the heat generation. It at any given point, right? And the same at the heat generated at the center. And the RF is the radius of the fuel, and the R is the distance from the center. So we have not going to the log down in what B is. B is just the constant, right? So uneven distribution of heat, that seems like that's key part of the problem.